Hi, my name is Gabriel Rueda, and this is my tech demo for presentation. So for this tech demo, there are three plots that are required to graph and show. The first one being this vector field with cos x and cos y in the y, in the x, and sine y and sine x in the y for the gradient. And then um, in the second one, there's a torus with these specifications, and then for the third one, it is a portion of this torus um, with these specifications here. So we'll get right into it. For the first one, for the vector field, I used GeoGebra, which has a pre-made sort of applet or function that I found that can plot vector fields very efficiently. This one, this is the author, and it allows you to input the um, the x part of the gradient in this first part here, and then the y part of the gradient in this part here. And as you can see, it's cos x and cos y in the x part, and sine x and sine y in the y part. And so you just fill that in here, and then here you can specify the bounds. So in this one, it requires -5 to 5, and then in both directions. And then this one, you can tell it how many vectors you want in each direction. I just set it to 10 and 10 so it's easier to see. And then this just controls the size of the arrows. And so as you can see, it creates this kind of swirly pattern that goes every pi, essentially. So through the center, it goes from -pi/2 to pi/2, and then it's pi in height for each of these kind of swirls. Um, and some interesting flow lines along this. If you're doing a square around one of these um, swirls here, the circulation will be positive because if it's in the counterclockwise direction, because it is not curl free and it is not path independent. Um, and around a point in one of these centers, which would be, for example, pi/2 or 0 pi/2. Here, the circulation around that would be non-zero. Um, and then moving on to the torus, that would be plotted here in Desmos. And there's a specific function to plot a torus. Specifically, this one right here, where this one is centered around the x-axis, and so it would be the square root of z squared plus y squared here, and then minus, you're subtracting it from the um, radius of the torus from the center to the center of the tube that goes around. And you imagine like a bike tire or something like that, and it would be the radius from the center here of the whole donut or the whole bike tire to the center of the tube, and that would be this like radius right here. And then this entire thing is squared here, and then you add it to x squared, and then you equal it to the radius of the tube. So you can kind of see it here. This would be a circle here. If we were to take a cross section, this is kind of the best I can give right now. But this radius right here is 2. So from the center being 4 down to the edge, which is 2, that radius is 2. And that is squared. I could have just written 4 here, but it's easier to see kind of what the values are. And so the general formula would be it being centered around x would just be square root of z squared plus y squared minus the big radius all squared plus x squared equals the tube radius squared. And so that's what that would be. And that's what this asked. And then for the portion of the torus specified here, it asks for x being greater than the square root of 2, y being greater than 0, and z being less than 0. And so here, I simply rewrote the same equation to plot this previous torus with the limitations of x being greater than root 2, y being greater than 0, and z being less than 0. And when I turn that on, it looks like this. So it just shows this portion. I can take this big one away, and it just shows this portion. As you can see, it meets those bounds as previously stated. And so to do these boundaries, you can specify that with parentheses or with these braces that can limit the range of each variable. All right, and that should be all. Thank you for watching. Goodbye.